In our third video of capital budgeting principles, we now turn our attention to why the net present value technique is preferred to the internal rate of return technique. We learned in the last video that the NPV provides a better ranking of mutually exclusive projects. Another reason is that the IRR technique can yield multiple internal rates of return. And then thirdly, the NPV makes a better reinvestment rate assumption, a more realistic reinvestment rate assumption. So in this video, we want to explore these three advantages of the net present value technique. Let's begin with the first one on ranking mutually exclusive projects. NPVs, the net present value technique, can be used to rank mutually exclusive projects. And the reason you want to rank them is you want to identify the best project. You want the one that ranks as the most valuable project to the firm. And we learned in the last video that IRR should not be relied upon to correctly rank mutually exclusive projects. In some cases, the project with the highest IRR may not be the project with the highest net present value. And that was the case with the two projects we looked at, Project S and Project L. To see why then, let's go back to projects S and L that had the cash flows that we see below here. This is the same example we looked at in the second video. And let's assume that projects S and L are mutually exclusive. We'll actually explore them as independent and mutually exclusive, but we'll really hone in on the idea of when they're mutually exclusive. Okay? Now, if we were asked to compute the NPV for each project as a function of the cost of capital R, so in other words, we're not going to put in yet a specific number for the cost of capital. We would just write the general NPV equations that you see on your screen there, where you're taking the initial investment. Look at Project S here. The initial investment is a $10,000 cash outflow. And then we're taking the present value of the cash flows in years 1 through 4, discounting them at the cost of capital, simply labeled as R. And we do that for both projects S and L. Now, the NPVs for each project for costs of capital ranging from 0% to 15% are reported in the table below. So I simply started off by putting for project S 0 in here, came up with the NPV, and then I put 5% in, came up with the NPV, and so forth. By the way, if you're doing this on your calculator, once you go through the entering of the cash flows, the gold clear all, 10,000 plus or minus CS of J, then you put in these cash flows hitting CS of J. Once you've done that, you can then punch out these NPVs very quickly by going 0 I per year gold NPV, 5 I per year gold NPV, 10 I per year gold NPV, and so forth. You don't need to keep entering the cash flows over and over again. Then once you finish with S, then hit gold clear all, enter the cash flows for project L, and then do the same thing, 0 I per year gold NPV, 5 I per year gold NPV, and so forth. So you can actually come up with these numbers fairly quickly. Now, what we want to do is graph the NPVs for each project as a function of the cost of capital. Okay, and it's going to create what's known as an NPV profile for each project. And we do that on the next slide. So you can see I've put the cost of capital, the discount rate, on the horizontal axis. I pushed a 15 above. We're going to see it kind of comes in right here. And I want to have the line and a little symbol over laying on top of the 15%. That's the only reason that's up there. And I've got NPV on the vertical axis. And then I plot the points here for project S. And you can see if I go back here, let's just look at two of the numbers. At 0% was 3,000. At 5% was 1,804. So there's the 0%. We're on this axis, 3,000. And at 5%, and I just kind of cited that in loosely, about 1,804 is the NPV. These are the next 2 points. And I'm not using a real sophisticated drawing tool here, so it's a little kinked. This should actually be a very smooth curve, but the next one's going to look even worse. But there's the NPV profile for project S. It's simply showing us the NPV as a function of the cost of capital. Now, what's interesting about this point right here where I have the cursor? Well, that's the discount rate, because we're measuring here, cost of capital. It's the discount rate that makes NPV equal to 0. It must be the internal rate of return for project S. And we estimated or computed the internal rate of return in the previous video at 14.5%, and that sure looks like it's around 14.5% to me. Okay, now we do the same thing for project L. Here at 0%, it was 44.50. At let's go back a second. At 5%, it was 2,500. That's about where that point is there. You can continue, you can pause this or go back and look if you want to. Those are the next 4 points. And again, that's a little more kinked than the previous one because it's more vertical, but it's got more curved linear nature to it. But if you can, just think of that as a smoother curve, not a kinked one with just 3 line segments coming together. But that's the NPV profile for project L. And again, what's significant about this point right here? Well, that's going to be the IRR for project L. And we computed that in the last video, and we got 13.5%. Okay, before we go further with this, let's just review our decision criteria for projects that are both independent and then mutually exclusive. And show you I can read them right off this graph. Suppose, initially here, suppose the projects are independent. And I'm going to show you why you can use both NPV and IRR. Let's assume the cost of capital is 10% and the projects are independent. Well, you can see that at cost of capital 10%, both have positive NPVs, so both are acceptable projects. You can also see that both have IRRs that are higher than the 10% cost of capital. If the cost of capital is 15%, we would reject both projects. Both have negative NPVs, and both have IRRs less than 15%. Now, if the cost of capital is 14%, right in between there, we would accept project S, the blue project. We would reject project L. Why? At 14%, S has a positive NPV. It also has an IRR higher than 14%, but project L at 14% cost of capital has a negative NPV and an IRR less than 14%. So hopefully by that you can see the consistency between the NPV and IRR techniques for independent projects. But what if the projects are mutually exclusive? And we're going to see the conflict that we saw at the end of the last video. At a cost of capital of 10%, project L has the higher NPV. I believe that was $942 versus $788. But project S has the higher IRR. See the conflict? L has the higher NPV, S has the higher IRR. So you get a conflict between the two methods. Now, we concluded in the last video that you should use the NPV technique because it identifies the project with the most value that's expected to be added to the firm if that project is implemented, and that choosing projects based on NPV is consistent with shareholder wealth maximization, maximizing the value of the firm. Okay, so as long as you're to the left of this crossover point, there's going to be a conflict. That crossover point, we'll solve for it in a little bit, is actually 11.7%. So if the cost of capital is less than 11.7%, the project with the higher NPV will have a lower IRR. Okay, now I'm just going to repeat a number of these points that I showed you while we were on the video. So there's a conflict between NPV and IRR if the cost of capital is left of that crossover point, 11.7%. That's where the NPV for project L exceeds the NPV for project S, but the IRR for project S exceeds the IRR for L. And we've concluded the NPV is the superior method for these mutually exclusive projects because NPV represents net value of that project. Selecting the project with the highest NPV is consistent with the objective of maximizing shareholder wealth. If the NPV profiles intersect, IRR should not be used to rank mutually exclusive projects to the left of any crossover points. And rather than graphing out just to determine whether we're to the left of that intersection, that crossover point, I would just say don't use the IRR. Just use NPV when you have mutually exclusive projects. And by the way, we have two projects here in the graph. Let's go back for a second. And we have one crossover point. If I had three projects, I could have multiple crossover points. You know, another one graphing in here could intersect both of them or one of them or what have you. So you can have multiple crossover points. Now, let me also point out that this is not the usual case. I think more often than not, the NPV profiles will not intersect, but I've constructed a case here, and I'll show you why they intersect in a moment, but I've constructed a case that's not the common case where they do intersect, but it's important to realize that they can intersect. All right, to solve for that crossover point, what you would actually do is set the NPV equations that are expressed as a function of r that we had written a few slides ago, and then solve for r. Here was the NPV expression for project S. Here's the NPV expression for project L, both expressed as a function of r. Well, what's true at the crossover point? What's true at the crossover point is that the NPVs are equal, right? Right there where they intersect, that's the same NPV. I don't know what it is, but it's the same NPV. Solve for the discount rate that makes NPV equal for each project. So that's what I've done here, is I've written the equation for the NPV for S as a function of R, the NPV for project L as a function of R, set them equal to each other, and you would solve that for R, and it's a mess. It's a trial and error iterative solution. If you work through that, you get 11.7%. Now, I'm going to show you a shortcut, but I'm going to show you where the shortcut comes from. In solving for this, I can recognize that I can add 9550 to both sides, right? Or let's say it this way, I can subtract negative 9950 from both sides, like saying it that way better. I can subtract the 1000 over 1 plus r from the 5000 over 1 plus r. Subtract the 3000 over 1 plus r squared from the 4000 over 1 plus r squared, and so forth. I can subtract term by term to simplify this. Can you see that I'm actually subtracting, if I do it this way, this from that, this from that, this from that, and so forth? Well, let's just go ahead and do that from the get-go without writing the equation out. Okay, and that's what I do here. The shortcut for determining the crossover point is to compute the IRR of the incremental cash flows. So I've written up the cash flows for S and L, and then I've formed a third column, or fourth column if you will, for the incremental cash flows. And I took the cash flows for S minus the cash flows for L. You can do it the other way around, doesn't matter. You can do cash flows from L minus cash flows from S. So I wind up with negative 450 if I take negative 10,000 and subtract negative 9,550, 5,000 minus 1,000, 4,000, and so forth. Notice it changes sign. And I get these incremental cash flows. Now, just solve for the IRR of the incremental cash flows. Just treat this like it's a project, if you will. Set it up as an IRR equation. We're solving for the discount rate, which is the IRR. Notice in solving for the IRR, we solve for the discount rate that makes the NPV, if you will, equal to 0. So I've just repeated the equation there. Go to the calculator, gold clear all, 450, make it negative CSJ, enter the cash flows, make sure you put the last two in as negative, because remember those last two are negative cash flows. And then hit gold IRR per year. Now depending on, I think, which version of your calculator, or it might be all of them, I'm not sure. With the HP10, you may get an error solution on this. And if that's the case, you just have to go to Microsoft Excel and do this. Okay, and the reason is you get more than one change in sign. We're actually going to explain that next as another weakness of IRR. Okay, so if we plug in 11.7% as a discount rate here, we would get that equal to 0. And that is indeed the crossover point in that graph if you go back and look at it. Okay, so there is one advantage of the NPV over IRR. You can rank mutually exclusive projects. Now, let's just ask a quick question. Why would NPV profiles possibly intersect? I mentioned a few moments ago that that's not the normal case. I think more often than not, they will not intersect. But what could cause them to intersect? Well, I can think of two reasons. First of all, timing differences in the net cash flows. Let's go back for a second. It's going to take me a moment to go back to the two projects. Well, here are the cash flows right here. Here are the cash flows for project S. Here are the cash flows for project L. Notice the initial investments are pretty much the same, pretty close. But notice the cash flows for project S start large and get smaller. The net cash flows for project L start smaller and get larger. That's going to make the slopes of the NPVs differ as you change the cost of capital. Okay. The one with the higher cash flows earlier will have less of a slope, or say it this way, the ones that have the large cash flows later, smaller cash flows earlier, will have a steeper slope. Okay. The NPV for project L is going to be more sensitive to changes in the cost of capital, and we saw that in the graph. See, L is steeper. With the cash flows, the majority of the cash flows received late in the project is going to have a steeper NPV profile. With the cash flows received sooner, it's going to have a flatter NPV profile. And when that happens, they can intersect. Returning back to where we were. The second reason is differences in scale. You can have a small project. Let me give you a ridiculous example, but I think it shows the point. And to ignore time value of money, let's assume we have a 1 minute project. You make the initial investment, and 1 minute later you get the final cash flow. It's just a 1 period project. So you invest something and the project's over a minute later. So I can ignore time value of money over 1 minute. If you invest $1 and a minute later your return is $2, that's 100% IRR. But the NPV is only $1. If I instead invest $100 and 1 minute later it's worth $110, the IRR is 10%, much lower than the 100%, but the NPV is 10, a much higher NPV. So, and again, that's a contrived and kind of a really ridiculous example, but it does illustrate that smaller projects have an opportunity to generate larger IRRs or higher IRRs, but have lower NPVs because it's just a small scale. Where the larger project can generate more NPV because of the amount of cash flows involved, but yet have a lower IRR. And that's, again, why they could intersect. And that's not very common at all for mutually exclusive projects to have two alternatives where the investment scale, the scale of the project is so different. But it could make an intersection occur. Okay, so we've talked about the first reason why the NPV is superior, and that is NPV can be used to rank mutually exclusive projects. IRR should not be relied on. Let's move on now to the second advantage of the NPV technique, and it has to do with this concept of getting multiple IRRs. With the depending on the number of sign changes, I'll explain that in a second, you can get more than one or multiple IRR. Let's define what we mean by the idea of normal cash flows. Normal cash flows for a project would have one change in sign. You'd have an initial investment as a negative cash flow, or simply cash outflow, net cash outflow, which is followed by positive net cash inflows. So here we have a net cash outflow at time 0, followed by a series of positive net cash inflows. I have one change in sign from negative to positive. It stays positive. When you have one change in sign, you'll get one IRR, and life is good. Economically, this IRR means something to us. It represents the rate of return, if you will, using time value of money that's received on this initial cash outflow, the initial investment. Non-normal cash flows would have more than one change in sign, where the initial investment is a cash outflow, a net cash outflow, followed by positive net cash inflows, and then at least one other negative net cash outflow out there somewhere. So something like this. Initial investment, cash outflow at time 0, followed by net cash inflows, and then another cash outflow, and then an inflow. Why could you have a negative cash outflow? Maybe it's a planned expansion. Maybe you start with an intermediate size project, knowing that after 4 or 5 years there's going to be such demand that you would have to maybe double or increase the size of the plant, and you'll have more of an outflow that year than you get from inflows, and then you start operating again. That's one reason. There's other reasons I could cite, but notice how many changes in sign there are. It goes from negative to positive, that's one change, positive, negative, 2 changes, negative back to positive, 3 changes. You could have 3 IRRs. It's just a mathematical thing. It's those of you who have studied more math, you may recall what's called Descartes' rule of signs. That's all this is. When we solve for the IRR, we're solving for the roots of a polynomial expression, and the number of roots of that polynomial expression can be equal to the number of sign reversals, which in this case is 3. So bottom line, I'll go back to speaking English here. If you have multiple changes in sign for the cash flows, you can get multiple IRRs. And when that happens, economically, those IRRs may not mean anything. They mean something mathematically, they're the roots of the polynomial expression. But from a financial or economic standpoint, those IRRs, if there's 2 or 3 of them, simply don't mean anything. Don't use them. So caution, don't use the conventional IRR technique when you have more than one change in sign and cash flows. NPV, no problem. Simply make that a negative cash flow, add the present value of these cash flows, subtract the present value of that cash flow, and add the present value of that cash flow. So the NPV handles this with no problem whatsoever. So projects with non-normal cash flows may have more than one IRR. The number of IRRs is normally equal to the number of sign reversals in the stream of cash flows. When more than one IRR occurs, none of the IRRs is meaningful in an economic sense. Use the NPV method for the non-normal cash flows. Just change the sign on those cash flows that are negative. The third disadvantage of the IRR, or I'll say the third advantage of the NPV, and this was more of a technical one, less important than the other two. There's an assumption made when you do time value money calculations. We don't really talk about that much, but NPV calculations, when you're doing a present value calculation, assume that those positive cash inflows over the life of the project are reinvested at the cost of capital, which is an opportunity cost principle here. It's assuming they're reinvested at that cost of capital. The IRR method assumes the cash inflows over the life of a project are reinvested at the IRR for the project. This may not be a very realistic assumption, especially for projects that have really high IRRs. You have some project with a 48% IRR. Well, to actually earn as a realized yield an IRR of 48% would require that those cash inflows that are received in years 1, 2, 3 through year end are reinvested at 48%. If they're instead reinvested at something closer to the project cost of capital, which is more realistic, of say 12%, you won't earn 48%. Now, it's not going to be a lot lower than 48 if that happens. It would be lower. It's not always a realistic assumption. Whereas reinvesting at the NPV is reinvesting net cash flows at the project cost of capital, which is what the NPV assumes, is a pretty realistic assumption. So we're left with a question here. If the IRR has these flaws or weaknesses, we've identified 3 reasons why NPV is superior to IRR, then why use IRR? I think it's a very good question, and I'm not going to advocate for eliminating using the IRR. Well, the IRR has one very important advantage. It gives us a better intuitive feel for the relative profitability of a project. If a senior executive who's never studied finance has someone from finance come to her and say, we have a project here with a net present value of $350,000. Well, put yourself in the shoes of that senior executive, although you've studied finance, of course. Well, you know it's positive, and I guess you might know theoretically that's acceptable, but just how profitable is that project? Well, if it was a $300,000 initial investment and a $350,000 NPV, that's a large NPV. But if it was a $2 billion investment with a small $350,000 NPV in that case, it's not that much of an NPV. The relative profitability is not so high. But if that person from finance came to you and said, hey, the IRR is 48%, you don't need a degree in finance to understand that's a very attractive rate of return. So the IRR technique gives us just a better sense, a better intuitive feel for the relative profitability of a project, because it's not just an absolute dollar amount that NPV is. Just knowing an absolute dollar amount for NPV just doesn't really give us a good signal for the relative profitability. Okay, that ends our third video in this series on capital budgeting.